4, 5, 6, 7, 8, 9. That's pretty good. One person missing. Okay, well, let's look at our schedule on the ICR. Oops. Okay, so last week we got most of the way through chapter 1. We got to finish that little bit that's left today. So I checked, everyone did the introductory quiz. Thank you. So then today we're supposed to move on to chapter 2, about chemistry. And I had a chemistry lab, this biological molecules lab, scheduled for today, but I didn't think you guys were all going to show up. I had a class at 8:10 this morning, and only 8 out of 24 students showed up. So I didn't expect 9 out of 10 of you to show up. So I didn't get that lab ready. Instead, I prepared for the microscope lab that I had scheduled for next week, because that's easier to set up and do. So I guess we'll do that one, do the microscope lab, and do that biological molecules lab next week. So chapter 1. So we went through this introductory stuff, some definitions, these chemical levels, or these levels of organization at which we can study human anatomy and physiology. Talked about the organ systems a little bit that we're going to be covering in this class. Features of living organisms that are not in non-living things. And then we learned some terminology, especially these are very important on this page. These terms. Should know what prone and supine mean. And these sections or planes, sagittal, frontal, and transverse, we need to know what those are. And the cavities, we talked about cavities, right? A little bit. Yeah. I'm gonna Come on. Why wasn't? Click on that, nothing happens. Okay. I won't do that anymore. It's annoying. Okay. So I need to know the body cavities, the pleura, the pleura and pericardium are the double membranes surrounding each lung and the heart, respectively. So each lung is surrounded by two pleural membranes, or two pleura. The one on the inside, directly in contact with the lungs, is the visceral pleura, and the one out to the outside of that is the parietal pleura. Same with the heart, surrounded by pericardium or pericardial membranes. The visceral one on the inside, and the pericardial, or the parietal to the outside. So visceral to the inside, parietal to the outside. A thin layer of serous fluid, the slimy lubricating fluid in between those two membranes. The abdominopelvic cavity is surrounded by the peritoneum. Again, two membranes. The inner one is the visceral peritoneum, and the outer one is a parietal peritoneum. Shown here again. Then we covered these regions and quadrants, two different ways of dividing up the abdominopelvic part of the body into either 9 regions or 4 quadrants. Yeah, and then I said, don't worry about this medical imaging stuff on this PowerPoint. You don't need to learn that for this class. And there was a handout, one handout that was a worksheet, right? That I said you should try to work through that. Any trouble with any of those? We're all able to figure them all out? Most of this is pretty straightforward, but the one, what's the right handout? I think this is the right one. Maybe I didn't have any leftovers. But probably the most tricky ones were the question about what kind of section you would cut through. Oh, like the heart in both lungs, or what was the other one? The brain in both ears or something. Be able to, anybody have any trouble figuring those out? Not sure. Okay. Well, I guess we'll move on to chapter 2, chemistry. And again, because I thought there would be a lot of people absent, I'm recording this. I'm trying to record this. Come on. I don't know. So what I'm recording will just record what's projected and my voice. So after class, that it takes a little while for the collaborate to process the video, but then it'll show up on Moodle. They'll under this week's module, you just click on it. It should take you to the video if you want to see that. Okay, chemistry. Chemical level of organization. Any of you guys had a chemistry class, a chemistry course in high school or college? No? Well, it's important to know a little basic chemistry to be able to understand physiology, because physiology includes a lot of chemical reactions. I'm not a very good chemist. Never liked chemistry. I always felt like I didn't really get it. I could learn it and pass the exams, but I never really. It just seemed so abstract. I didn't really get it. But and I struggled with it. I had to take you have to take pretty much chemistry to be a biologist. I had to take like 3 years. If you major in biology at a university, you have to take at least 2 whole years of chemistry. I think I'm pretty good at teaching chemistry, even though I'm not a very good chemist. And I think because I had so much trouble learning it, that when I'm explaining it, I feel like I'm trying to explain it to somebody who was as dumb as I was when I was trying to learn it. So I try to make it as simple as I can. And I had one student, an older student. She was about 50 years old, and in an anatomy class a few years ago, and she had a degree. She had a 4-year college degree. She said she told me that she had taken a whole year of chemistry, but after just my 3-hour lecture on chemistry, she said she understood it better than she ever did after taking a whole year of it, because I explained it so simply. So I hope that's true. Okay, what is chemistry? Study of composition of matter and how it changes. So what's meant by matter? Matter says anything that has mass and takes up space. So matter is just physical stuff. And for an example of something that is not matter is energy, because energy does not take up space. It doesn't have mass. Matter is made up of elements, and elements are just different forms of matter. And the examples of elements are some of them here: oxygen, carbon, hydrogen, nitrogen. You've heard of all of those. They're different kinds of matter. And what's the difference between oxygen and carbon, or carbon and hydrogen? It's the kind of atoms that make up those elements. And that's what much of this chapter is about. What is an atom, and what makes one atom different from another, and how do atoms interact with each other to form molecules? A molecule is just 2 or more atoms stuck together. How does that happen, and why does that happen? So there are over 100 elements. just 4 of them listed here. And living organisms like us normally contain only about 25 of the 100 elements. And so here's a list of elements that occur in the human body, and they're listed in order from the most abundant. So the most abundant element in your body is oxygen. So the body is 65% oxygen, 18 or so percent carbon, and hydrogen, nitrogen, calcium, phosphorus. So these are the most abundant elements that make up your body. The ones that say trace elements, that just means there's just tiny amounts of them in your bodies. But they are, even though there's only tiny amounts of them, they are nevertheless important. You probably recognize some of these if you buy a jar of multivitamins with minerals to take as nutritional supplements. You'll see on the label a lot of these things because we have to have them in our body all the time. Just tiny bits, tiny amounts of them. But if one of them is missing, it can cause serious health problems. So, okay, well, I'm going to skip ahead to this thing, the periodic table. There's most labs, chemistry and biology labs, have one of these on the wall somewhere. So that's what this is, and so this it's just a chart with all the elements on it, and so every element has a symbol. That's 1 or 2. In a few cases, there's three letters. So it's a capital letter and a lowercase letter, and some cases 2 lowercase letters. But in many of them, the symbol is the first 1 or 2 letters in the word, the name of the element. But not in all cases. So, for example, H is for hydrogen, He is helium, and lithium and beryllium, boron, carbon, nitrogen, oxygen, so on. But some of them don't seem to make sense, like Fe. That's iron. There's no Fe in the word iron, but the Fe is from the Latin word for iron, which is ferra. In fact, metals that have iron in them, like steel is a mixture of iron and some other metals, and that's called a ferric metal because it has iron in it. This one, K, is potassium. Again, that's from the Latin word for potassium is something like kalim. And what else? Sodium, Na, it's from the Latin. Or sodium is natrium. In fact, we'll mention later in this class that there's a condition, medical condition called hyponatremia. Hyponatremia, that natrium in it. Hypo means low. Natrium means sodium. So what do you think's wrong with that person who has hyponatremia? Yeah, not enough sodium in his body. Hypernatremia would be what? Too much. Same with the K. K is from the Latin for potassium, kalim. There's a condition called hypokalemia and hyperkalemia. So you don't have to learn all of these, certainly, for this class. But we'll talk about what these numbers mean in a few minutes. But, okay, but we need to go back and okay. So I talked about the symbols. So this would be oxygen, carbon, hydrogen, nitrogen, calcium, and said that a molecule is two or more atoms stuck together, like H2O, that's water, right? It has two, it's written like this, H2O, that's water. That means a molecule of water has two hydrogen atoms and one oxygen. So if there's no subscript, that means one, right? So this is a molecule, three atoms stuck together. It's also a compound. Water is also a compound because it's made up of at least two different elements, right? So it has hydrogen and oxygen in it. So that means it's a compound. But something like, you've probably seen this on a tank of oxygen that they use in hospitals or people with breathing problems. It has this on it, to O2. That's because the oxygen most of the oxygen in the air and in a tank of oxygen, it's not just oxygen atoms by themselves, but they're in molecules of two oxygen atoms stuck together. And in a few minutes, we'll see why that happens. Why would two oxygens want to be stuck together? But this is a molecule. It's two or more atoms stuck together. But is that a compound? It's only one element, right? So it's not a compound. It has to be at least two different elements in that molecule for it to be a compound. So this is both a molecule and a compound. This is a molecule, but it's not a compound. So other examples of the way molecules are written with the symbols. So NaCl, that's just one sodium and one chlorine atom stuck together. So anybody know what NaCl is? Sodium chloride. Do you ever use that for anything, you think? May have used some today for breakfast. Salt, yes, just salt, table salt. This one, C6H12O6. Bet nobody knows that one. Anybody? Yeah, glucose, good. Yeah, glucose, that's sugar, right? That's what your blood sugar is, glucose. So it's 6 carbons, 12 hydrogens, 6 oxygens all stuck together in one molecule. Seems like that would be a pretty big molecule with all those atoms in it, but that's actually, many molecules are way, way bigger than that. That's really still a relatively small molecule. And this one, H2O2, what is it? Yeah, hydrogen peroxide, yeah. Okay. So what is an atom? It's made up, each atom is made up of 3 particles, protons, neutrons, and electrons. And let's look at a diagram. So here's a diagram of an atom, or this one on the first slide. Yeah, this is good. So this is a diagram of an atom. So the protons and neutrons are in the center. They're in a cluster of particles in the center. It's called the nucleus of the atom. We'll use that word nucleus when we study cells in the next chapter, chapter 3. So a cell has a nucleus also. That's where the chromosomes are in a cell. So don't be confused by the cell, the nucleus of an atom and the nucleus of a cell. It's the same word, but completely different meanings, right? So, but the nucleus of an atom, that's where the protons and neutrons are in the center. But then out here, you see these little guys that are spinning around in these orbits, kind of like the planets around the sun. Those are the electrons. These protons and electrons have a static electric charge. So the word static means not moving. So it's not like electricity flowing through a wire. or anything. It's just a static charge that's attached or part of the particle. So electrons have a negative electric charge, protons have a positive electric charge, and the neutrons have no electric charge. So we say they're electrically neutral. That's why they're called neutrons, right? So protons and neutrons are about the same size as each other, but electrons are much tinier. An electron is only about 1/2000th the mass of a proton or neutron, but the negative charge on an electron is the same size as the positive charge on a proton. So it's just one's negative and one's positive. So what makes an atom of oxygen different from an atom of carbon? Different elements. It's the number of protons, neutrons, and electrons. Most importantly is the number of protons. The number of protons determines what element an atom is. And that's called the atomic number. Atomic number, the definition of that, just how many protons are in an atom of a particular element. So here's helium, a very small atom, just has 2 protons, 2 neutrons, and 2 electrons. So these are just 2 different diagrams showing the same thing, trying to describe an atom. So the atomic number of helium is 2. There's 2 protons in that atom, so atomic number of helium is 2. If an atom has any number of protons other than 2, then it's not helium. Because that's what defines helium. It's an atom that has 2 protons. Normally, the number of electrons is the same as the number of protons in a normal atom. That can change because atoms can lose or gain electrons. We'll see in a minute how that happens. But if there's the same number of negative electrons as positive protons, then the overall electric charge for that atom is neutral, right? Because they kind of cancel each other out. There's the same amount of negative electrical charge as positive electric charge. So we say that the net electric charge, or the total electric charge for the atom, is 0 or neutral. Right? So this atom has two electrons, and this circle here represents the orbit, like the planets moving around the sun in this circle. But they don't stay exactly that distance away from the nucleus. They can move closer and farther, But this is the average distance out from the nucleus that these 2 electrons will spin. This different diagram of showing the same thing, it shows a cloud. It's just so the electrons can actually be anywhere in this area, but the average distance is represented by this circle. So just 2 kinds of diagrams showing the same thing. The number of neutrons in this case is the same as the number of protons, 2, but that's not always the case. In most atoms, the number of neutrons is different from the number of protons. Okay, so the number of protons is called the atomic number. The mass number is the number of protons plus the number of neutrons added together. So in this case, it's 4. This 2 plus 2 is 4. That's the mass number. Then this word isotopes, you may have heard that word before. So these are atoms of the same element, but they have different numbers of neutrons. So the number of protons always the same for an element. And I said the number of electrons normally the same as the number of protons, but it can change because atoms can lose or gain electrons. but the number of neutrons can also vary. So in most elements, there are isotopes. So an example of carbon 12, um, that has a mass number of 12, 6 protons and 6 neutrons. So most of the atoms of carbon in the universe are carbon 12. Like 99% of them are carbon 12. But there's a few of them out there that have 8 neutrons instead of 6, and so that would be 6 plus 8 is 14, so that's called carbon 14. There are some that have 7 neutrons. That'd be carbon 13. So there are at least 3 isotopes for carbon. Same element, but the number of neutrons is different. This one is what we call a radioactive isotope. I'm sure you've heard that term. Radioactive isotope is one in which the nucleus has particles flying out of it. So if this was a radioactive atom, then once in a while a proton would come flying out of the nucleus. And why would that happen? What do we know about opposite electrical charges? How do they affect each other? Or are they attracted to each other, or do they repel each other? Opposites attract, right? Opposites attract. Yeah, if they're the same charge, they repel each other. They push each other apart. Right? These are negative electrons, positive protons in the nucleus. Why don't the electrons get sucked into the nucleus if the opposites attract? Similar reason why there's gravity between the sun and the planets, but why don't the planets get pulled into the sun by gravity? It's because they're spinning in orbits, and the centrifugal force keeps the planets out in their orbits. Same thing here. These electrons are spinning around here so fast that they don't get sucked into the nucleus by attraction of opposite charges. But what about this? If like charges, the same charges push each other apart, how can these protons stay in the nucleus like that? Why aren't they pushing each other out, pushing away from each other? That's actually a question that I'm not smart enough to understand the answer. I know the answer kind of, but I don't really understand it. That's you've heard of nuclear physics. That's what nuclear physics means, the physics of the nucleus of an atom, what's going on in there. And that's the kind of thing that people like Albert Einstein studied. And Albert Einstein figured out why these protons don't push each other apart. There's a mysterious force in the nucleus of an atom holding these positive protons together. And so there's a lot of energy stored in the nucleus of an atom. That's why if you split the nucleus of an atom, a lot of energy is released. That's how atomic bombs work in nuclear power plants. You can get a lot of energy out of a very small amount of radioactive material, or just by splitting nucleus of atoms to release the energy. You can make a lot of electricity from a very small amount of radioactive material. But so we're not going to worry about that, because in chemistry, we care more about the electrons than the protons, because it's the electrons that form the chemical bonds. They're involved in the chemical bonds for holding atoms together. The protons and neutrons normally stay in the nucleus and don't do anything much, unless it's a radioactive one. If it's radioactive, then then this nucleus is not stable. That mysterious force in there isn't holding them together enough, so once in a while this proton comes flying out. So if an atom loses a proton, then it's a different element. So that's called radioactive decay. When an isotope has protons flying out, it changes into a different element. And those particles that come flying out are so high energy they can hurt you. That's why we cover that radioactivity. Okay, this term atomic mass. So we learned about atomic number, mass number, and atomic mass. So what's that one mean? Well, if we look at this periodic table again, there we see these numbers. These numbers in the upper left corner, that's the atomic number, the number of protons in the atom. But down here at the down here there's another number. It says 12.0107 and 14.0067. Those are that's the average of the mass numbers of all the atoms of that element in the universe. And so, for example, we saw that that helium has 2 protons and 2 neutrons, so the mass number is 4. But here's a number that says 4.02602. What? It's just a tiny bit above 4. Why that is almost all of the atoms in the universe of helium have 2 neutrons, but there's a tiny few of them out there that have 3 neutrons. So their mass number would be 5 instead of 4. So this number, 4.002 something, that's if we would average the mass numbers of all the helium atoms in the universe. Most of them are 4, but there's just a few of them that are 5 that would raise the average up, so it's a tiny bit above 4. So that's what that atomic mass is. So, but don't worry about that. I'm never going to mention that again. You need to know atomic number and mass number, but don't worry about that atomic mass. That just has to do with isotopes. Okay, what else? Okay, so here's another atom diagram. So it tells us it's got 11 protons, 12 neutrons. So plus sign means positive charge, 0 means no electric charge. These are electrons with negative sign. But there's 3 circles here, 3 orbits. And that's because something we have to know, we have to learn, is that the first or the innermost orbit can hold only 2 electrons, so 1, 2. If there's more than 2 electrons in an atom, then the other electrons have to be in other orbits farther out. So the second orbit has 8 electrons, and that's all it can hold. Second orbit can hold up to 8. The third one can hold up to 8, but it has only 1. So this one it says 11 protons, and 2 plus 8 plus 1 is 11 electrons. So like normally, the number of electrons same as the number of protons, but the electrons are arranged in these 3 orbits. Another word for the orbits is electron shells or energy levels. Those 3 mean the same thing. Electron orbits, energy levels, electron shells. So we need to know, remember, the first shell holds up to 2, second shell holds up to 8, Third shell holds up to 8. And that's important. We'll see why in a minute. But first, let's go back to the periodic table again. So we saw that list of 25 or so elements that are in living organisms like humans. All of those are up in the top part. All of those important elements in biology are in the upper part of this periodic table, like hydrogen, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, phosphorus, sulfur, chlorine, and so on. But I think the farthest one down is iodine. That's normally in humans. We have to have iodine to make our thyroid glands work, right? But none of these down here are in living organisms normally. I mean, not supposed to be. But I mean, here's mercury down here, and here's lead, and arsenic is down there. So they do. I mean, we probably have, especially if you eat a lot of tuna, you have mercury in your body. It's not supposed to be there. It's a toxin. You don't want to have too much of it, but it doesn't belong in your body. All the normal ones are up here. So this rule about 2 electrons in the first shell, 8 in the second, 8 in the third. That's all we need to know for biology because none of the elements that we care about in biology have more electrons than that. So elements that have like 70 electrons, they're not the ones that occur in biology anyway. So we don't care about, once you get more than this number of electrons, like 4th and 5th shells, it gets more complicated. It's not as simple as just 8 in each shell. It gets more complicated. But for us, as biologists, this is all we need to know. 2, 8, 8. Beyond that, there's larger larger atoms. We don't care about them anyway. So, why is this important? A chemical reaction, you've heard the expression chemical reaction. A chemical reaction is just, if you put 2 atoms together, it makes a molecule. Or if you put 2 molecules together, they'll form a bigger molecule. Or other chemical reactions are breaking molecules apart into smaller molecules or into atoms. But if you mix 2 things together, there won't always necessarily be a chemical reaction. Sometimes there will be, sometimes there won't. Depends on what we're mixing. What determines if something is going to have a chemical reaction? It's whether or not the atoms are stable. The word stable in chemistry means that an atom is happy like it is. It's happy the way it is. It doesn't want to form a chemical reaction. It's just happy the way it is. And what makes an atom happy and stable, or unreactive, or inert is another word. Inert means inactive. So an inert atom is one that doesn't want to have a chemical reaction. What makes an atom happy and stable is if the outermost shell of electrons is full of electrons. So this atom, this is sodium, and this atom, its outer shell has only 1 electron, and that shell can hold how many? 8. So it's not full. That means that atom is not stable. It's not happy like it is. It's reactive. If you mix If you mix sodium atoms with some other kind of atoms that are reactive and unstable, there will probably be a chemical reaction. They'll come together and form molecules or something. Um, but what about this one, helium? It has only one electron shell, right? Because it has only two electrons, and that shell can hold two. So is that stable? Yes. So in fact, there's no such thing as a molecule with helium in it. Because helium, no matter what you mix helium with, it will not have a chemical reaction, um, because it's happy like it is. Um, Atoms form chemical reactions with other atoms in order to get their outer shell full, so that they become stable. And another, what about this? So this is hydrogen. These are just isotopes of hydrogen, but just ignore that. This is normal hydrogen. Um, uh, just one proton and one electron, no neutrons. So is that stable? That one shell is not full. It has only one electron, can hold two. Hydrogen is very reactive. And in fact, we could use hydrogen as fuel for our cars, because hydrogen burns. Burning is a chemical reaction between some kind of fuel like hydrogen and oxygen. If you put oxygen and hydrogen together and put a spark or a flame to it, it'll burst into flames. And um, it would be a really good fuel for our cars, because what would come out the tailpipe in the exhaust? If you mix oxygen and hydrogen, what do you think you'd get? You get this. So you just have water vapor come out the tailpipe, no pollution. But we don't use hydrogen because it's too expensive and too hard to make pure hydrogen and to compress it into a tank, a fuel tank. Okay, so a story about hydrogen versus compared to helium. Hydrogen's reactive, helium is stable, unreactive. You ever heard of the Hindenburg disaster? What that's about? So the Hindenburg was the name of a big airship, like a big blimp, and they used to fill them with hydrogen gas. Hydrogen and helium are both very small atoms, so they're lighter than air as a gas. So that's why they float. So they filled this big airship with lots and lots of hydrogen, and hydrogen being very reactive and flammable, it just took a spark and the whole thing went up in flames, and 20-some people on board all died in that disaster. What do they use now in those? Helium. Same thing in the party balloons you buy at Dollar Tree, right? It's just helium. Better. It's much better, because helium is inert, inactive, stable, won't burn no matter what. Much safer. So that was a very hard lesson that was learned about the difference. This word valence electrons are just the electrons in the outer shells. So like this would be the valence electron in this sodium atom, the one in the outermost shell, because those are the ones in the outer shell. Those are the ones that participate in forming bonds with other atoms. And so how and why does that happen? Let's look at this hydrogen. Let's see, do we have diagrams showing? Well, here's some just more diagrams. Comparing hydrogen, which is unstable, helium, which is stable, lithium, unstable. It's got 4 in that shell, could hold 8. Neon is stable. So in fact, let's look at that periodic table again. I keep coming back to this. Why are these arranged in this table in the way they are? They're not just, it's not just a random list. These are arranged that way because in each row, the rows are called periods. That's why it's called a periodic table. In each row, there's the elements or the atoms have the same number of electron shells. So hydrogen and helium, they both have just 1 electron shell, right? Because this one has 1 electron, this one has 2. Then starting in the next row, this has 3 electrons, so it has 2 electron shells. 2 in the first shell, 1 in the second. This has 4, 5, 6. So these all in this row or period have 2 electron shells. This row, these all have 3 electron shells, 4, and so on. And in the columns, they all have the same, all of them in each column have the same number of electrons in the outermost shell. So this has 1 electron in the first shell, this has 1 electron in the second shell, 1 electron in the third shell, and so on. And these over here, this column, these all have their outermost shell full. So these are all stable. In fact, these are called the inert gases, inert meaning stable, unreactive. So helium, neon, argon, krypton, all of them, they don't form molecules. They mix them with each other or with anything else, there will not be a chemical reaction because they already have their outermost shell full. So what about hydrogen? Said that almost all the oxygen in the air is just like this, 2 oxygens stuck together. Same thing with hydrogen. The hydrogen in the air surrounding us right now, most of the hydrogen is in pairs, like H2. These are called diatomic molecules. Diatomic just means 2 atoms. And so why would they do this? Well, hydrogen, it's unstable, has only 1 electron. It would like to have 2 electrons in that shell. So what if two hydrogen atoms would come together? So here's 1 hydrogen, it's got 1 electron. What if another hydrogen would come next to it? It also has 1 electron. And what if they would share those electrons? So, so instead of the electron just spinning around this proton and this one around this proton, what if the electrons would spin around both like a figure 8? Sharing those electrons with each other, now it's as if each one has 2 electrons, right? As long as they're sharing them like that, and as long as they're stuck together like this, they're sharing those electrons, so it's as if each one has 2 electrons, so they're stable. So this is what we call H2. So this is one way that 2 atoms can come together and form a molecule in order to get their outer shell full and be stable and happy. It's just like married people are always happier than single people, right? Oxygen does the same thing. Oxygen normally has 6 electrons in its outer shell. It needs 8. So, and two oxygens would come together. It's a nucleus. And they would share 2 pairs of electrons. So each oxygen would share 2 electrons with the other one. And again, it'd be, the electrons would be spinning around both. And So that's what we call a double covalent bond. The word covalent, we haven't defined that yet, but there would be sharing two pairs of electrons to form O2. Okay, so um, yeah, this rule of the 2 in the first shell, 8 in the second, 8 in the third, that's called the octet rule. Oct means 8 of something, like an octopus has 8 appendages. Um, so chemical reactions. So in a chemical reaction, 2 or more atoms come together to form a molecule, and they're held together by what we call bonds, chemical bonds. So this sharing of electrons forms a chemical bond that sticks those 2 atoms together. So the 2 kinds of chemical bonds that hold atoms together in molecules: ionic bonds and covalent bonds. Covalent bonds are just this. So valent means the electrons in the outermost shell. Co means together. So 2 atoms share some of their valence electrons together to form a molecule. This is called a covalent bond. This one. The other type is called ionic bonds, and first of all, we need to define this word ion. Said earlier that and normally the number of electrons is the same as the number of protons in an atom. But an atom can gain or lose 1 or more electrons, and then it becomes what we call an ion. An ion is just an atom that has gained or lost 1 or more electrons, or a molecule that has gained or lost 1 or more electrons. So if an atom loses an electron, now it has less negative charge than positive charge, so the total charge on the atom will be positive. So if it loses an electron, then the atom has a positive charge. We call that a positive ion or a cation, just a positive ion. And then we put a plus sign next to the symbol. So this H plus, that means a hydrogen atom that has lost an electron. Sodium atom that has lost an electron, so it has a plus sign. This one, calcium, has lost 2 electrons, so it has a 2 plus sign there. If an atom gains an electron, it becomes a negative ion, or called an anion. So examples: chlorine, Cl minus, fluorine, F minus. And we said opposite charges attract. So what would happen if a positive ion and a negative ion came close to each other? They would stick. That's an ionic bond. That's all there is to it. Simple. And so some molecules are held together by covalent bonds. Some are held together by ionic bonds. And an example of these are covalent bonds. Water molecules held together by covalent bonds, but sodium chloride, NaCl, that's held together by an ionic bond. And let's look at how that happens. So here's a sodium ion. Remember that one? We saw that one earlier. It has 1 lone electron in its outer shell, all alone out there. So this is unstable. Fluorine has 7 in its outer shell. So it's also unstable. They would both like to have 8 in their outermost shell. So if the sodium would just lose that 1 electron out there, then the second shell would be the outer shell, and it would be full. Now that sodium atom would be stable and happy. The chlorine, if it would just gain 1 more electron, its outer shell would be full with 8. It would be stable. So when these come close to each other, that's what happens. This one electron will jump off the sodium onto the chlorine, which is glad to accept it. And now they're both stable, but now they're both ions. One has lost an electron, the other's gained an electron. So this should be a plus sign, any plus there. So this is positive, this is a cation or positive ion. This is an anion, a negative ion. So they are attracted to each other and form sodium chloride. And we use this symbol NaCl as if it's one sodium atom and one chlorine atom together, but these form many molecules that are held together by ionic bonds. They form crystals, and so sodium chloride or salt does this. So instead of just one sodium and one chloride, it'll be a whole bunch of them in this three-dimensional arrangement. So sodium, chlorine, alternating in all three directions. That's what we call a crystal. And this is why if you look at a grain of salt under a microscope or just a magnifying glass, it looks like a little box because it has this crystal structure of the arrangement of the sodium and chlorine atoms. Molecules that are held together by ionic bonds, if you put them in water, dissolve them in water, they come apart. The sodium, like you put this in water, the sodium and chlorine separate from each other into the water. Covalent bonds don't do that. Put them in water, they don't come apart. In fact, water itself is held together by covalent bonds. Okay, so that's ionic bonds and covalent bonds. Covalent bonds can be polar or nonpolar. So what's that mean, and who cares? These would be what we call a nonpolar covalent bonds. The word polar means something is different at both ends, at either end. Like the Earth has a north and south pole. A magnet has a north and south pole. Like one end attracts, like you turn two magnets toward each other. One way they'll push each other apart. One way they'll attract each other because they have different poles. Bipolar disorder, two opposite moods. A person is either too happy or too depressed. A polar covalent bond would mean that one end of the molecule is different from the other. But in H2, there's no reason why the one end of this molecule would be different from the other because it's symmetrical. It's the same on both sides of the bond. These electrons will spend about the same amount of time spinning around this hydrogen as around this one. So that's nonpolar. But in a polar covalent bond, the electrons are shared unequally between the atoms in the molecule. And the classic example of a polar molecule is water molecule. So where's the picture? Okay, this is a water molecule, diagram water molecule. So oxygen, two hydrogens, and in a water molecule, the hydrogens are at an angle like this. They're not opposite each other, but these are just three different kinds of diagrams of a water molecule. But these are covalent bonds between oxygen and hydrogen here. So this bond is sharing one electron from the hydrogen with one from the oxygen, but there's two of them. That way, each of these hydrogens, it's like it's gaining an electron. This oxygen is gaining two electrons. So they're all three of them are stable when they're in that molecule. But these electrons that are shared between this hydrogen and this oxygen, they're not shared equally. So these electrons they're spinning around the hydrogen maybe one time, and then around the oxygen maybe 3 or 4 or 5 times, and then the hydrogen one time. Why would it do that? It's because, again, opposites attract. This hydrogen atom has just one proton, one positive proton in its little nucleus. Water has 8 positive protons, and because the negative electrons are attracted to the positive protons in the nucleus of either of these atoms, this one has a bigger positive, has more positive charge in it, so it's going to attract these shared electrons more. This has only one positive proton, so these electrons are going to spin around the oxygen more times, fewer times around the hydrogen. So the same thing with this hydrogen. So because these electrons spend more time around the oxygen than around either of the hydrogens, the oxygen end of the molecule is said it's weakly negative, and the hydrogen end of the molecule is weakly positive. That's what this weird symbol means. That's a Greek lowercase delta, Greek letter delta. So in chemistry, that symbol with a plus sign means a weak positive charge. This means a weak negative charge. Like it's not a whole electric charge like an ion, but it's just because these electrons spend more time here than here. This end of the molecule is a little bit negative, and this end is a little bit positive. So that makes these polar covalent bonds, and this is a polar. We say it's a polar molecule. Positive at one end and negative at the other. Why is that important? Because in liquid water, there or in any covalent molecules, there are weak attractions between the molecules. So this remember, this is the hydrogen end is a little bit positive. The oxygen end is a little bit negative. Again, opposites attract. So the positive end of this molecule is attracted to the negative oxygen end of this molecule, and these weak attractions are called hydrogen bonds. And I wish we didn't use the word bond for that, because it's not like a ionic bond or a covalent bond that holds atoms together in the molecules. This is just a weak attraction between separate polar molecules. So in liquid water, there's a whole bunch of these water molecules, and they're all polar, so they're all attracted to each other. It's like they're all being weakly pulled toward each other a little bit. And this gives water some of its important properties. Some of them you already know about this. You know that if you have a container, you fill it with water, you fill it all the way to the top, you could add a little bit more, right? The water will pile up above the rim. How is that possible? Gravity is trying to make it spill over, but it's like it has a skin over the top of it that's preventing it from spilling over. If you add a little bit more, it eventually will spill over, but what's letting it pile up that way? There's a term for that. Anybody know what that's called? You've heard of surface tension? You've seen insects that can walk on water. It's like they're walking on a skin on the surface of that water. Why don't they just sink? It's because of this hydrogen bonds between these are all water molecules in here, all with hydrogen bonds, including at the surface. It's hydrogen bonds between them that makes it like a skin on top of the water. It's called surface tension. Non-polar stuff doesn't have hydrogen bonds. because the molecules are not polar, there's no positive and negative end to be attracted to each other. So an example of something nonpolar is oil, gasoline, kerosene. Those are all nonpolar. So in gasoline, there's no attraction between the molecules because they're not polar. And if you try to do this with gasoline, you can't do it. If you fill it up to the rim, but one more drop, it'll spill right over. There's no surface tension in gasoline. An insect cannot walk on the surface of gasoline. There's no surface tension. So why if you mix water and oil or gasoline together, you stir it, you shake it, no matter how much you mix it, it won't mix. They won't dissolve together. Even if you get it, looks like it's mixing, and then you let it sit for a minute, what's going to happen? They'll separate, right? Usually the water will be at the bottom, the oil or gas will float to the top, just because water is heavier or more dense than oil or gasoline. And why does that happen? It's because we have a picture, a diagram. Yeah. So these are the water molecules, and these other round ones are something like oil, nonpolar. So if you mix them together, mix all those molecules together, and then you let it sit, what will happen is the water molecules have hydrogen bonds pulling them toward each other, so they're all pulled together. The oil, no hydrogen bonds, they're not attracted to each other or to the water, so they'll just be squeezed out of the way, and they'll just float to the top, the water will float to the bottom. So nonpolar stuff mixes with other nonpolar stuff, like oil and gasoline. Will they mix? Can you mix them? Sure. In fact, there are some kinds of engines, gasoline engines, that you have to mix some oil with the gasoline to put it in the tank. They're called two-stroke engines. That oil is necessary for lubrication. And anything that's polar will mix with water. Like sugar molecules are polar; they'll mix with water just fine, right? But polar and nonpolar don't mix with each other. Other things about water, that these hydrogen bonds are important. So water is different from a lot of other liquids, other materials. One thing different about water or unusual about water, is it's lighter, less dense as a solid than as a liquid. That means that ice floats. Why doesn't ice sink? Most other substances that occur in both liquid and a solid, the solid part is heavier and it'll sink. So like we would have had a container here of steel, metal, that we got it so hot that it melted, so it's liquid. And then we had a chunk of solid steel, and you drop that in there, it would sink to the bottom. But in water, the solid is lighter, it floats. Water has a high heat capacity, which means it takes a lot of energy to raise the temperature of water compared to other liquids. And that's because of hydrogen bonds. The heat energy in a substance like a liquid, like liquid water, the heat is just movement of the molecules. In a liquid like water or gas, like the air surrounding us, these atoms and molecules are always moving, bouncing off of each other constantly. And that energy is heat. So the faster they're moving, the more heat energy, the higher the temperature. So if you put water on a stove, turn the burner on, so heat energy is going into the water, it takes a lot of energy to get that water hot. compared to something like gasoline. Don't do this, but if you put gasoline on a stove, you have a pot of gasoline and on one burner and a pot of water on the other burner. Same amount of heat being delivered by both burners. The gasoline would heat up much faster because the water molecules, the heat, adding more heat to get the water molecules moving faster, but there's hydrogen bonds holding them together. So it takes more heat energy to get them moving faster compared to gasoline, which has no hydrogen bonds. Okay, we'll take a break sometime, I guess. A couple minutes. What else? Okay, let's just do this and then we'll take a break. So some words here: solution, solute, solvent. A solution is just something dissolved in a liquid. The liquid is called the solvent. Could be water, could be oil, it could be alcohol. And a solute is what's dissolved in it, usually something solid that dissolves in it. But there could certainly be more than one solute. But for example, salt water. Water is a solvent, salt is a solute. But we could also put sugar in there, and it would dissolve, and there would be two solutes. But they would form a solution. So these terms, hydrophilic and hydrophobic, these refer to what I've been talking about with polar molecules dissolve in water, so they would be called hydrophilic. It just means, it literally means water loving, it means they like to dissolve in water. Hydrophobic means they hate water, or they're afraid of water, they don't like to dissolve in water. So that would be oil, gasoline, anything, stuff that doesn't dissolve in water would be hydrophobic. Okay, let's take a break. Feel like 11:45 or so. And we'll spend the last hour or so looking at microscopes, playing with microscopes a little bit. So who's not here? Raise your hand if you're not here. So, Michaela here? Okay. William, Mallory, Catherine, Rylan, Megan. Ariana is not here, but Abby, Michaela, Zamaripa. Okay, that's okay. Okay, well, let's talk about a little more of this chemistry, and then we'll get up and do some stuff. Okay, this a symbol like this, and we got a molecular formula. It just tells us what are the elements and how many of each, but that doesn't tell us anything about the shape of that molecule. But a structural formula tells us a little bit more information, and it tells us about the shape, so or the structure of the molecule. So this would be H2, 2 hydrogens. This dash represents a single covalent bond, so sharing one pair of electrons. Oxygen, double covalent bond, sharing 2 pairs of electrons. Here's water, and these are covalent bonds. Carbon dioxide. This tells us that the carbon is in the middle and the oxygens are on either side. So that tells us something about the shape of the molecule. This one, glucose. Both of these are glucose. Glucose can be in 2 shapes. It can be a straight chain of carbon atoms with other stuff attached, or this can curve around to itself and form a ring shaped molecule like that. Still C6H12O6, but different shape. Chemists use shorthand. So this symbol means the same thing as this. And wherever there's a corner without a symbol, you assume it's carbon. This one has an oxygen, an O for oxygen, so we know this one is something else. It's oxygen, not carbon. Okay, I need a little bit more about chemical reactions. What you have before the chemical reaction happens, we call the reactants. And then after the chemical reaction, we have products. So the reactants could be two molecules and then the products would be one larger molecule formed by those two combining, or the reactants could be one molecule and the products could be 2 molecules after breaking that reactant molecule apart. So there's different kinds of reactions. Synthesis, the word synthesis means to make something. So this is combining 2 things to make 2 molecules or 2 atoms, or an atom and a molecule to make a bigger molecule. Decomposition, just the opposite, breaking a molecule apart. An exchange reaction would be both. So it'd be breaking these 2 molecules apart, and then the parts of those molecules come back together in different combinations. So just rearranging the atoms into different molecules. Reversible, it has an arrowhead at both ends, and that means it can go in either direction depending on circumstances. It often could be, if there's a whole lot of A and B, then the reaction would go this way. But and then there's a high concentration of this stuff, then it would go the other way. This word catalyst just means the word catalyst in the English language just means something that causes something to happen, but in chemistry, it's something that causes a chemical reaction to happen or speeds up a chemical reaction. So the catalyst is not one of the reactants in the reaction because the catalyst is the same before and after the reaction. It just speeds up the reaction. It doesn't. It's not. Doesn't take part in the reaction, or it's not changed itself. In a chemical reaction, there's all the elements before the elements in the reactants will always be the same as the elements in the products. So do something like combine hydrogen and oxygen, and you get water. Always going to be the same. The same elements will be on the left side of the arrow. The arrow represents the reaction. These elements will be the same as these elements. So there could never be something like this. Hydrogen plus oxygen produces carbon dioxide, because the carbon's on the right, but it's not on the left. Hydrogen's on the left, but it's not on the right. So elements don't change. They just rearrange or come together or separate in a reaction. This word electrolyte is important in anatomy and physiology and medicine. So it's a substance that releases ions when dissolved in water, like sodium chloride. You put it in water, comes apart into sodium ions and chlorine ions. Use the word chloride for ions. So this will be a chloride ion, even though it's an ion of chlorine. Sodium chloride is an electrolyte. In medicine, we would often refer to these as the electrolytes. The real definition is what you put in the water to release these ions. But in medicine, if you're monitoring the electrolytes in a patient, what you're actually monitoring is the ions, not really you're not going to monitor this. You're going to be monitoring the sodium, chlorine, potassium, calcium, all those ions in the body fluids of the patient. And that's really important because, especially in children and babies, because they're so small. If they're vomiting or have diarrhea, they can be losing a lot of electrolytes really fast, and their electrolyte levels can change, and that can be fatal. It's really important that all these ions, sodium, potassium, chlorine, calcium, magnesium, they have to be at the right amounts in your body. That's part of homeostasis. And if there's an imbalance, there's too much or not enough of one, it can upset the physiology so much that it could be a medical emergency. Okay, we need to learn about acids and bases. So this would be a container of pure water made up of just water molecules. So water molecule, water molecule, water molecule, and again, they're always moving around, bouncing off of each other. And sometimes when they hit each other, one of those molecules can break apart. The water molecule can break apart. When a water molecule comes apart, it forms these two ions, H plus and OH minus. So this is hydrogen that has lost an electron. This is called hydroxide, OH minus. This happens all the time. Water molecule breaks apart. But then sometime later, this H plus and another OH minus might come together and form a water molecule again. So they're always breaking apart, coming back together. But at any moment, in any given moment in a container of water, some of the water molecules will be broken apart. And so there would always be the same number of H plus as OH minus, right? If there's 100 water molecules in here that are broken apart right now, then there would be 100 of these and 100 of these. But what if we would add more H plus? So now there's more H plus than OH minus. Now that's what we call an acidic solution. Acidic, as in acid. That's all. That's what's really meant by acidic. Just means there's more H plus than OH minus in a water solution. And so what you would add to that water to make it acidic, we call an acid. So something like this, HCl. This is hydrochloric acid. That's the acid that you have in your stomach. And this is an electrolyte, which means if you put it in water, it comes apart into ions, right? So add this to pure water, it's going to come apart, it's going to add more H plus to that solution, so making that solution acidic. So it's not pure water anymore, now it's an acidic solution. Nitric acid, another acid. It's an electrolyte. You put it in water, it comes apart, adds H plus to that solution, makes it more acidic. Right? So an acid is just something that you add to a solution, and it makes it more acidic. The word base is the opposite. A solution is basic if it has more OH minus than H plus. And something that you add to a solution to make it more basic is called a base. For example, sodium hydroxide, and that's lye. Put that in water, it comes apart into Na plus and OH minus. So it's adding OH minus. So now there's more OH minus than H plus in that solution. So we call that a basic solution. The word alkaline means about this almost the same thing. The chemist would say, no, it's not exactly the same thing. It's almost the same. This milk of magnesia, magnesium hydroxide. Put it in water, comes apart. It's an electrolyte held together by ionic bonds. So you put it in water, it comes apart. It's adding more OH minus. So that's also a base. In fact, that milk of magnesia is people take it to settle their stomach. And how it works is if you got too much acid in your stomach that's irritating your stomach, then this will neutralize the acid. So make this your stomach juices less acidic, more basic. So pure water is not acidic or basic. We'd say it's neutral in between. And this pH, you've heard of pH, this is a measure of how acidic or basic a solution is. And it's just a measure of the concentration of H plus in that solution. It's like how many H plus ions per milliliter of that solution or something. But it's a number from 1 to 14, and so yeah, this is what you need to know. High pH means this seems kind of backwards, but the high pH, the higher this number, the pH number, the lower the concentration of H plus. So these square brackets in chemistry mean the concentration of that. So this means the concentration of H plus how many H plus ions per milliliter or something of that solution. So if it has so if a solution has a very low pH, that means it's very acidic and has a lot of H plus. If it has a very high pH, that means it has less H plus than OH minus, and it's basic. And right in the middle is 7. Right in the middle of that range from 1 to 14 is 7. That means we say that's pH neutral. It's not acidic or basic. It's pure water. So the pH of pure water is 7. Anything below that is acidic. Anything above that is basic or alkaline. So here's some familiar solutions and their pHs. So at the very, very high or above 7 means it's basic. So blood is a little bit basic, 7.4. Seawater, more basic, 8. Baking soda, ammonia, bleach, drain cleaner. The higher the number, the more basic. And below 7, so milk is a little bit acidic, coffee more acidic, grapefruit juice, soda, tomato juice, 2.5 to 3.5. Lemon juice, pretty acidic, pH 2. Then battery acid, battery acid, that's sulfuric acid in a car battery. And hydrochloric acid, like in your stomach, very strong acid. We know that strong acids can burn you, but very strong bases can also burn you. If you get some, just like drain cleaner on your hands, it can burn you just as bad as an acid. Something that, a property of bases, like mix baking soda and water or ammonia, bleach. You ever get that stuff on your hands that feels real slimy and soapy? It's hard to rinse off. That's typical of bases. Acids are not like that. They don't feel soapy. And if you mix an acid and a base together, you'll get something with a pH in between them. So if you get battery acid on your skin, you need to, if you want to neutralize that, you would use one of these bases, like baking soda. That white crud that builds up on the car batteries sometimes, where the battery cables are connected to the battery posts. That's people typically use baking soda, but mix baking soda and water to clean that off. It neutralizes the acid. What else? Okay, a buffer is a buffer is a chemical that, if it's in a solution, it helps to keep the pH what it is. So if a solution has a good buffer in it, then if you add some acid or base to that solution, the pH will not change very much. We have buffers in our body. That's why buffers are very, very important in biology. So, for example, the pH of human blood needs to be in this very narrow range. If it gets below or above that, you are in what we call alkalosis or acidosis. That's part of homeostasis, keeping your pH of your body fluids in that narrow range. But what keeps it there? What if you drink 3 glasses of lemonade? It's very acidic. Is that going to cause your blood pH to drop and get very acidic? It won't, because your blood has good buffers, good buffer systems. And we'll learn about that when we do the chapter on blood. Okay, well, I don't know if we should just talk a little bit about organic. What's meant by organic in chemistry? Um, the word organic has different meanings. It can mean lifelike or living or natural. You go to Walmart and the produce section and they got organic bananas and they got regular bananas. The difference is organics are more expensive, right? But organic in that context, organic means natural. So those fruits and vegetables are grown without chemical fertilizers, without chemical pesticides. So they should be healthier. But that's not what organic means in chemistry. Chemistry, organic means carbon compounds. So organic chemistry is a chemistry of carbon. And they use the word organic because in the early days of chemistry, there were these certain compounds like proteins and carbohydrates and fats and oils that these chemists, they only found them in living organisms. They never find proteins in a rock or non-living, something non-living. They were only in living organisms. And so it was thought that 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 they could only exist in living organisms. Only living organisms, the cells of living organisms could produce those kinds of compounds. Chemists had no idea how they could do it in a lab, make a protein in a lab, um, or um, uh, synthetic make oils in a lab. Now they do that all the time. Um, but back then, that's why they call them organic. They were only in living organisms. They could only ever be in living organisms. But now, all these years later, now um, the whole plastics industry is based on making these organic compounds in labs and factories. But they still use that old term organic. It's just like a leftover term. Um, so an organic compound is a compound that has carbon, that has at least one carbon and at least one hydrogen attached to that carbon. So this, well, we already saw this one, glucose C6H12O6, has carbon and hydrogen. That's an organic. That sugar is an organic compound. Um, this CH4, that's methane. That's the smallest, simplest organic compound there is. Just one carbon with four hydrogens attached with covalent bonds. This carbon dioxide has carbon but no hydrogen, so this is not considered to be organic. It has to have both carbon and hydrogen. So this and anything that's not organic, we call it inorganic. Inorganic substances, so examples: water, oxygen, carbon dioxide, salts. Those are all inorganic. Okay. Of course, water is important in living organisms, especially humans. Oxygen, carbon dioxide, very important. And salts, we already talked. Well, the word salt just says an electrolyte that can be formed from reaction of an acid and a base. But the table salt, sodium chloride, is a salt. But salt is, there's a lot of different molecules that we call salts, or compounds we call salts, but they're typically electrolytes. They're held together by ionic bonds. Like sodium chloride, magnesium chloride, sodium fluoride, they're all just ionic molecules. Okay, the organic compounds, there's many, infinite number of organic compounds. Carbon is a very versatile atom because carbon has 4 electrons in its outermost shell, So that means a carbon to become stable. It's unstable by itself, but it could form covalent bonds with 4 hydrogens around it. Each one would share 1 electron with the carbon because it has 4 empty spaces in its outermost shell, so it can form 4 covalent bonds. But these could be it could be 1 oxygen and 2 hydrogens, or instead, or it could be nitrogen and oxygen. It's just any combination of 4 covalent bonds around it. So many kinds of organic compounds. Many organic compounds are in long chains of carbons with other stuff attached, hydrogens, maybe oxygen and the oxygen has hydrogens attached. There's many kinds. And if you go to university and major in biology, you have to take a whole year of organic chemistry. I had to do that. There's a whole year of carbon, because carbon compounds are so important in living organisms. Something I kind of skipped over that's important concept is I said that atoms come together to form molecules to become stable. So then they're not reactive. So how could this, how could this chemical reaction happen? Remember I said you could burn oxygen, you could burn hydrogen in your car engine. And burning is just a chemical reaction of a fuel like hydrogen with oxygen. How could that happen if I said these are both stable? They're stable because that's why they're together like this, so they'll be stable. How could there be a chemical reaction if they're both stable? Why would they? I said they're happy like they are. What causes a chemical reaction in between 2 stable molecules like this is something has to cause these to come apart from each other. What's going to cause them to come apart? Heat. That's why if you mix gasoline and oxygen together, it's not going to burst into flames. But in your car engine, it does, because there's spark plugs in there that make a little spark. That spark causes the 2 oxygens to come apart, and now these separate oxygens are unstable. Now they'll react with the gasoline. So if you put heat or fire or a spark to this, just enough to get some of these to come apart and some of these to come apart, now there will be a chemical reaction, the burning, and that burning produces more heat that causes more of these to come apart. Now these are all getting unstable, and then now they're ready to react. So let's call it the activation energy for a chemical reaction. Sometimes you have to add a little energy to get it started. And once it gets started, it'll continue on its own. Okay, well, there's many organic compounds, but the important large organic compounds, kinds of organic compounds in living organisms like us are these 4: carbohydrates, lipids, proteins, nucleic acids. You're familiar with some of these. You know what carbs are and proteins, probably. Lipids are fats and oils. They're non-polar. They don't mix. They're the kind of things that don't mix with water. And nucleic acids are DNA and another similar molecule called RNA. But those are what make up most of your body, these large organic compounds, and they're also what's in the food we eat, right? Because what do we eat? We eat other organisms that are made of the same stuff, same kind of stuff that we're made out of. So we need to go through each of those little bits, but we'll wait till next week for that. Um, maybe look at this on your own, and then we'll go over it next time. But now let's stop this and do some lab stuff for the rest of the time. So how many of you guys have used microscopes enough that some of you use microscopes a little bit? Fine if you haven't. Here's a handout. One of these. So you have microscopes in your little cabinets below your table. So grab one of them, pull it out. These microscopes that we have are called compound microscopes. They're very nice microscopes, unless you get a bad one. If you're starting to see you can't seem to get anything focused, you might have a bad one then. But they get serviced like once a year. We have somebody come and check them out. But so compound microscopes have this. It has a platform called the stage, and everything you look at on a compound microscope like this, it has to be on a microscope slide, which is this clear glass thin rectangle, and it goes on the stage, and when you put it on there, you pull this trigger, this spring-loaded trigger, you pull it back, and you put the slide in into this corner, and you release that, and it holds the slide in place. So everything has to be on a slide. You can't use this kind of microscope without the specimen being on a slide. So you can make your own slide, put something on there, and you can do that today. One kind of thing that's described on the handout is making a slide of cells from the inside of your cheek. Just scrape it with a toothpick, put that on the slide, put a drop of water on it, and put a cover slip, which is a thin little square of glass that goes over that. And that's what we call a wet mount. There's something else you want to make a wet mount of today, you can. You go outside and find a leaf or something. And we have prepared slides over here. Lots of different kinds of prepared slides. So these are slides, we have bought them. They already have stuff on them, different kinds of tissues or cells. And for practice, we have slides of the letter E. So it's a little E printed on the slide, just to practice focusing and stuff. And we have slides of colored threads also for that, just for practicing, focusing on them. So when you should lower the slide using these focus knobs. These focus knobs raise and lower the stage with the specimen on it, because these lenses are focused on just a thin layer of space and below the lens, and you have to get the slide right in that thin layer of space that's in focus. That's why you're raising and lowering with those focus knobs. So see, it's best to lower the stage all the way so you have room. You can rotate this nose piece to get this. Put the shortest lens over the stage. That's the lowest power. That gives you the most room between the lens and the stage to put the slide in there. Then leave it on the lowest power and you move the focus knob. I like to raise the stage all the way up, and then while I'm looking through the lenses, I slowly lower the stage using the focus knobs until the specimen comes into focus. And these two knobs hanging down from this corner of the stage, move the stage away from you and close to you and side to side. So you need to make sure the specimen is under the lens, first of all, or else you won't see it, of course. And you'll notice that everything looks like it's upside down and backwards. So if you move the stage this way, through the lenses, it looks like it's going this way. If you move it that way, it looks like it's coming toward you. If you get it focused on the low power, then go ahead and rotate the nose piece to the next power. Rotate clockwise, so go to the next higher power. It should still be pretty much in focus, but you might have to use the fine focus knob, the outer one, to get it in focus a little bit again. And then maybe if you want to go to the third one, the third lens, those are called the objective lenses, the ones that you can change. Go to the third one, might have to focus again. You might have to adjust the light. These have their own light source, so you plug it in and there's this little switch on the back for the light. And there's a dial on the side to make it brighter or dimmer. And also, another way to adjust the light is on the front of the stage underneath, there's a lever that swings back and forth. That's called the diaphragm, iris diaphragm. It closes and opens a hole below the stage to let more or less light in. So two ways to adjust the light. You might have to fiddle with both of them. To get the light just right. Usually at higher power, you need more light. So if you go from low power to higher power, you might still be in focus, but you might need to add a little more light. If you got too much light, it'll be too faded. If you've got not enough light, it'll be too dark. So that'll be playing with that all the time. If you ever, like you go from, you got it in focus, you go from low power to the next power, now you've lost it. You can't find it, can't get it in focus. The best thing to do, go back to low power and start over. It's much easier to find it and get it focused in low power than high power. The fourth lens, the longest one, it has the word oil on it. It's called an oil immersion lens. And that one, to use that one, you put a drop of oil on a slide on top of the cover slip, and then you actually lower the lens into the oil, and that reduces the amount of refraction or bending of light, because whenever light passes from one material to another, like from glass to air, it causes some blurriness. You lose some resolution. So having it go from light to oil, or from glass to oil to glass, it's less. You lose less resolution. You get a more clear image compared to going from glass to air to glass. But we're not going to use that. We got oil for that, but I don't like to even bother with it. It's too messy. It's not worth bothering with. So just don't even use that. The highest power lens, the oil immersion one. Just use the first three. So that's a compound microscope. One thing we need to know that'll be on the lab practical, I'm sure. How do you know what power you're looking? What magnification power you have? The objective lens has it on there. It'll have a number and a letter X, 4x, 10x, 40x. But these eyepiece or objective lenses at the top, they also have a number. I see 10x on there. So the total magnification is multiplying them together. 10x plus whatever you got, whichever objective lens you got. So if you got the 10x on here, times 10, that's 100. You got to multiply them together. So it's always, the objective lenses on all of these are 10. So you just multiply the objective times 10 and you'll have a magnification. So those are compound microscopes. This is called a dissecting microscope, and it's lower power. Doesn't really have a stage like that. You don't have to put the specimen on a slide. Um, you can. So these are good for looking at bigger things. These compound microscopes are good for looking at cells. They're very tiny. But this you can look at bigger things like insects and flowers, or even dissecting tissues under it. You can even hold the specimen in your hand and move it around while you're looking at it with a dissecting microscope. Um, this one, to change the power, you rotate this knob on top, and focus knobs are just like on the compound. Um, okay, so we got stuff for you to look at here. If you want to practice with the letter E slides, got them, colored red slides somewhere. Your colored threads, got slides of blood smears. If you want to make a blood smear of your blood, you can do that today. We'll do that later this semester. You have to poke yourself to get a drop of blood. Got just slides of cells, onion roots with cells, and fish eggs with cells. Um, if you want to do your cheek cells, the toothpicks, the slides, cover slips, it helps to put a drop of this blue dye, the stain on, to make the cells show up better. You can do that if you want. No droppers, put a drop of water on it. So just help yourself. This box is full of many different kinds of prepared slides, different kinds of tissues and stuff. Use them if you want. So it just go on up and get stuff. But while you guys are over here, let's do a quick, some quick chemistry. We'll do more chemistry next week. But how do you measure pH of a solution? That's what these are. These are called pH strips. pH strips or litmus paper. And it just has this colorful chart on it. I can't do this very well, but I'm colorblind. I can't match these colors up to the damage. So we have some stuff here we can test. I think it's some chemical loading, get some more cups. So this was pricey. And how about some baking soda? Baking soda and water. This is distilled water. Some of you want to take this strip out and test that? Here. And this is vinegar. Let's tear off these little pictures for me. Immediate. So we match that up with we're close to 9, so that makes it basic, right? It's above 7. That's what we expect. Baking soda is a base. When I was a kid, my dad used to put baking soda in water and drink it, and then that's stuff. The idea is to use it on as gas. but that was probably what's that thing. Okay, somebody want to try the vinegar? Put the stuff in the vinegar. Two. So vinegar is an acid, right? Vinegar is acetic acid in water. It's not as strong as hydrochloric acid or sulfuric acid, but it's an acid. And so here we've got lemon juice. Move down a little bit. And so we want to do this. So I think on the chart on the PowerPoint said 2 for lemon juice. So that's what we expect. This is acidic. If we get lemon juice in a cut or something, we know it burns, right? So one limitation on any kind of color coding tests like this is, what if we want to know the pH of grape juice? Do we use this for that? Why might that not be good? When put this in grape juice and pull it out, we're going to have a purple, because it has its own strong color. So sometimes it doesn't usually work good with stuff, solutions that have a strong color, because it could misleading results. Okay, one other thing to work with is kind of cool. This stuff is called phenol red. This stuff is it's red, right? And you mix some of that with water. I don't think it matters how much we put in there. So, I'm going to measure. So this stuff is sensitive to pH. I think it's red at pH above 7. But if the pH gets just a little below 7, it turns orange and then yellow. As soon as it comes from the basic, and the more acidic. So this demonstration is carbon dioxide. We're always exhaling carbon dioxide. Carbon dioxide dissolved in water forms an acid, carbonic acid. So if somebody blows through the soda straw into that, blowing their carbon dioxide into that, we should see if it's true that there is carbon dioxide in your breath. And as that carbon dioxide dissolves in the water, it should lower the pH of that water, make it more acidic, and it should turn from red to orange and then yellow. So we try it. Who wants to go? Need somebody to take a straw and sit in there and go. Why don't we go ahead and put the straw in there and put this on there so you don't splash it on your face. I don't think it's toxic or anything. You guys see it? Keep on. You change it? Change from red to yellow? So, yeah, I can see that. Oh, thank you. So pH became more acidic all the carbon dioxide in the breath. Okay, so let's play with the microscopes for the rest of the time. So just practice on getting finding the specimen and doing it focus, and going to the next power. I think there's instructions on the handout, but just basically you need one of those, and you just rub it on the inside of your cheek, and then rub it on center of the slide. And, now you can go ahead and put the cover stuff on. You get too much water coming out, then now you can just put this to absorb it. I'm going to use. Anybody having trouble getting started? Well, able to find your specimen and put this